Hi, in this video we shall see how to create a layout for the inverter circuit using the standard cell approach. In the previous video we had seen how to create layout using the um, generate all from source method. Like we went to connectivity and went to generate all from source. Like this we had created uh, earlier. Now we shall use the standard cell approach. For that I need to create layout cell view first, and then, as you know, in the standard cell library the height of all the cells will be same, only the width varies. So for that we will be calculating the height of the cell, um, and I will show it now how it is going to be calculated. So here in this course you will be designing 12 track standard cell library. That means you will be having 12 tracks totally, right? So there will be total of 12 tracks like this. But actually the VDD and VSS will be shared by adjacent rows and columns, right? So for that reason the VDD and VSS will be coinciding with the adjacent rows. It will be shared by adjacent rows, right? So this is one standard cell, and this will be your one standard cell, and this will be one more. So the VDD and VSS will be shared. So the contribution from VDD and VSS is only half each. So finally there will be 11 middle tracks, okay, plus half of VDD plus half of VSS. So totally 12 track library. So we need to draw 11 middle tracks and half of this VDD and VSS. So for that reason I'll take now M1 drawing, and then I will just randomly draw like this. Randomly in the sense the width, as of now I don't know the width of the inverter. So I'll just assume this will be my width of the inverter to take a starting point, right? And also you observe that the pitch line, this middle line of the metal path is coinciding with x-axis. Now I need to copy this 12 times. Instead of using copy I need to copy this 12 times with minimum DRC, right? So instead of doing copying it 12 times and pasting it, what I will do is there is an option called repeat copy. Okay, so using that I can easily copy it 12 times. Hmm. Um, uh, First, I need to select the instance and then click on repeat copy and then measure 32 nanometer from this. How much distance the next copy instance should be. Okay, then press escape and then copy and paste it here. And now I need to copy it 11 more times. Then simply press dot or full stop symbol in your keyboard. So now I have two tracks: 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So totally you will be having 13 tracks. Now as you had observed here, this VDD and VSS is going to be shared, right? So this that means the current that is flowing here is will be more. This VDD and VSS will be more. That means we should also increase its current carrying capability. Okay, that means we should make them less resistance, or in other words we should make them more wider. Okay, for that reason I will be increasing the width of these two metal lines VDD and VSS as 80 nanometer. Okay, now according to the minimum DRC rule, metal 1 to metal 1 spacing must be 32 nanometer. Now this is less than 32. So what I will do is I will select entirely like this and move upwards like this. Now there is 32 nanometer spacing between M1 to M1 of different mask. They should be of different mask. I should also need to color them or give the mask and lock them. And also I should be moving this one again. So first I will draw a scale of 32 nanometer and then move it like this. Okay, so now you can see uh, everything is done with respect to drawing of horizontal metal tracks. Just for the sake of verification, we'll once count all the how many number of tracks we have laid out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Right? So uh, each one of these middle tracks will be of 32 nanometer width, except VDD and VSS, which are 80 nanometer width. Right now, we know that mask 2 is always better than mask 1. So we have to keep the alternate metals uh, of different mask, and we need to keep VDD and VSS in mask 2 because mask 2 is always better than mask 1. So I have selected alternate metals like this and press Q and then select all and then select mask 2 color here and then lock it. Now they will start appearing green. Now I need to select the unselected metals, unmasked metals or uncolored metals like this and then select all here and then make them mask one color and then lock it like this. So this is the step 2, right? Then what we have to do is we have to draw poly pitch lines. So for that uh, we have different poly pitch lines like this. So we will be choosing the minimum or the smallest poly pitch possible, that is poly 86. And before that we need to draw actually the PR boundary, right? Uh, PR boundary, I will select this and enter into rectangular mode like this, and then I'll start from the origin and I'll end here. So now I have drawn my PR boundary like this. Okay, so now what I have to do is I have to draw poly pitch lines. So here you can see poly 86 actually, and press R to enter into rectangular mode. So the difference between these two is that you can see if you measure the poly pitch lines here, it is 86, whereas here it is 90. So that's what this purpose indicates, like poly 90 is 90 nanometer pitch width, right? So I will be using the minimum one, so I will just delete this and poly pitch 86. So from where to draw? From where I should start drawing? For that, we what we have to do is there is something called half DRC rule. Okay, so according to which we have to have that poly should appear, the poly line that will appear here should be half distance, like half of the distance from the PR boundary. That means first we need to measure 43 nanometer from here inside. And here my poly pitch line should start, the first poly pitch line should start from here, right? So here if it is like 43 and this is 43 because half of poly 86, okay, 86 nanometer, half of 86 nanometer is 43. So I should actually start drawing from here. Okay, and then I should here also the PR boundary should be in the middle of the poly pitch, but we don't know, we have randomly taken the width. So first we'll draw poly pitch and then adjust the right side PR boundary. Okay, so you have to make sure that the last poly pitch also is 86 nanometer, because there is a mistake of keeping it less than 86. You won't get to know. So just make sure that the last poly pitch is also 86 nanometer. Now what you will be doing is, um, just select, enable partial select, and then select the entire metal path along with the PR boundary like this, and then press stretch. Before that, I need to measure the midpoint of this poly, that is 43 nanometer from here, right? So I have marked the midpoint. Press escape and press yes, and start moving it and keep it here. So as you can see, here the PR boundary is in between, in the midway of these two poly pitch lines. Here also the PR boundary is in the midway of these two poly pitch lines. Okay, so now drawing of poly pitch lines and metal tracks are done. Also coloring of metal is also done. PR boundary also we have drawn. So the next step is, uh, we need to instantiate pfet and nfet. For that, I'll be instantiating pfet and nfet from finfet library p1svt, and I'll keep the number of fins as 3, because we know that from the circuit, right, it is 3 fins for inverter 1, 3 fins for a pfet of the inverter 1x, right? Then click on show layout parameters, then make this drawing only and keep this none. None, the dummy poly is not required, only keep left and right edge polys, and click on hide. Now you can keep it like this. You can, why I'm not keeping like this is because, as you can see here, if I keep it here, my poly is going out of PR boundary, right? So you can, I'll keep it like this and I'll show it to you. So here you can see my poly is actually going out of the PR boundary. That should not happen. So I'm just moving my uh, pfet inside the PR boundary, and I will disable this M1 tracks. As of now, I don't want them, right? So I'm just disabling them. And now you, as you can see here, the NVL and the PSVT is coming out, so that is not a problem. It is fine. Okay, so when there is an adjacent cell coming here, it will get overlapped, and the next poly edge that it will be coming here is here. So in that way, we are ensuring that the poly is always at 86. The poly pitch is maintained, and here from the next poly adjacent to it will be coming exactly here, right? So the poly pitch is maintained to be 86 nanometer. Similarly, we will instantiate N1 SVT also. Here the number of fins is 2, and similarly, layout parameters, I'll keep it none for the left and right dummy poly, and the dummy type purpose, I'll keep it drawing only, and keep it like this. Again, I should not, if I keep it here, it will be going outside the PR boundary. I should not do that, so I will start it from here. And as you can see, the first poly is appearing in the first poly pitch line like this. So for because of that, my NSVT, PSVT, and well will be going outside the left edge of the PR boundary, and that is fine. It will get overlapped by the adjacent another cell, adjacent cells, so it won't create any issue for us. Now as you can see, I am actually having these things, some this area is extra, I need not keep this, so I can actually stretch this inside, right? How much I should stretch now, that is the question. So here you can see, this is my first poly appearing, so this will be my last poly, right? So my PR boundary will be exactly 43 nanometer from here. This is the last poly pitch line. So my PR boundary will be exactly coming here. So now what I will do is I will enable partial select, and I have selected all these things and press yes to stretch them. Now I will be stretching like this. So now I will press Shift K to remove all the scales. Press F to fit to window. Now you can see I have instantiated pfet and nfet, and now the next step is to draw poly. Poly should be drawn from PR boundary, top edge of the PR boundary to bottom edge. Now I don't require M1, I'll just switch them off, and I'll start it from top edge of the PR boundary to bottom edge like this. Make sure that you align all this properly. There should not be any mismatch, like this should not be going outside or kept inside. Exactly, it should be touching the PR boundary like this, here and here. And I should do the same thing for these two poly pitch lines also. So what I will do is I will just select this, press C to copy, and then I'll keep it here. Similarly, copy, paste. We need not do on the edge here in this on these poly pitch lines, because imagine you will be having cells like this, and that will be that poly will be coming over here. So this you need not place any poly in this line, on this line. The polys are to be required only inside the PR boundary. As you can see, this is my PR boundary. The polys are required only inside the PR boundary. This is just a reference line. Poly pitch line is just a reference line. I need not put any poly over there. Outside the PR boundary, it is not required. So the next step is to join the uh, drain to create the output node, right? So the next step is to join this LIACT. So I'll enable um, okay, before that there are other layers that need to be done. Okay, so what I will do is I will just enable NVEL. So as you can see, this is my NVEL. So now my height is fixed, how much it is. So if I ask what is the height or what is the width, now you can easily tell my height is from top edge of the PR boundary to bottom edge, or bottom edge of the PR boundary to top edge, right? So you can see this is my height of the cell, 0.816 micrometer or 816 nanometer. And if I have to say what is the width, this is my width, 0.258, or you can also say that as 3 poly pitches. My width of the poly, how we say this is my 12 track library. Similarly, the width can be specified in terms of poly pitches, 3 poly pitch. Okay, so you can actually see that over here. So 0.258 divided by 0.086 nanometer is the poly pitch width, right? So you can see here. So I'm getting 3 as the answer. So my width is 3 poly pitches, height is 12 tracks, right? So now I have to have PSVT and NSVT and well, half of the cell I have to draw it, half of the cell, right? So NVEL will be covering half of the cell, NSVT covering the half of the cell, and PSVT half of the cell. So to calculate half of the cell, it's 0.816 divided by 2. So here you can see it is 0.408. So first I need to measure 408 like this, right? Then I will remove this scale. Okay, let it be. Later we will remove all scales. Now I will enable only NVEL and press R to enter into rectangular mode, and I will start from here. I will first enter into the click on NVEL, okay, and then start drawing NVEL. Press R to enter into rectangular mode and then start. Then I will just keep it like this I don't know how much. So now what I will do is I will extend this such that this will exactly overlap like this. Press F. Okay, now I will disable my envel, enable only PSVT, and then now what I will do is press R to enter into PSVT. Select PSVT and press R to enter into rectangular mode. And now I have to start from here such that from PR boundary it should be there, right? So from top it should be here, but I need to cover this one also. So first I will draw it like this. Then what I will do is I will just select the left edge of the PSVT and then keep it till this point and select this one, keep it till this point. So finally your PSVT should look like this. It's exactly half of the cell. Then I will enable NSVT and then similarly I will select NSVT and then start drawing like this, and I will keep it half of the cell. Now I will select this edge and I'll stretch it till this point. Similarly I'll do the same thing here also like this. Now press Shift key to remove all the scales. So this is how it looks when you enable PSVT and NSVT only, and when you enable NVEL, the NVEL and the PSVT will overlap. It is exactly like half of the cell. Okay, so now we will enable all the layers except M1. Okay, now we will have to join the LIACT layers. Press P to create path and now join this LIACT and LIACT. This is because the drain of the PFET and the drain of the NFET are shorted, right? This is my output node actually. Then press F. Now enable M1. Okay, now I have to connect my source terminal of PFET to the VDD. I'll do that now. I will actually disable NVEL, PSVT and NSVT. That is not required now. So as you can see, it is automatically creating the via M1 to LACT via. Similarly, I'll do the same thing here, right? Press F. Okay. So now, as you can see here, all the terminals have been connected. Gates are shorted, but the gate has to be connected to one of the metal strips, and the output node also has to be kept on one of the metal strips. How we are going to do is using vias. So poly should be connected to metal, right? So create via. To create via, the bind key is O and M1 to LIPO. Click on M1 to LIPO, hide, and you can keep on any of these horizontal metal tracks. It's not that you need to keep this one only, but the thing is, if you are given a choice, you always try to select mask 2 metal because mask 2 is always better than mask 1, as I had mentioned earlier. Select this, and now again we need to connect the LAACT layer to metal 1. Press O, then M1 to LAACT, click on hide. You need to place this via such that this uh, center point of the V naught actually coincides with your LAACT layer like this. Here also the center of the V naught should coincide with the pitch line, poly pitch line like this here. And it should be properly aligned like this. Okay, then press F. So now all the metal connections, terminal connections, everything is done. So, but still there are few problems. For example, As I had mentioned earlier, this will be overlapped, and see, I have my poly drawn like this. Okay, here also I have poly like this, continuous, right? So what will happen? This is my input, and this is also my some other input. So they are getting shorted actually. That is unwanted. That should not happen. Okay, so how we are going to avoid that? We shall see now. So first enable only poly. Okay, like this. Now I will be using cut poly to actually it will be drawn like this. Just start it from here, okay, and just keep it like this. Just keep it till uh, actually you need to keep it till PR boundary only. You need not I'll just enable PR boundary. So you need to keep it till PR boundary only, like this. Okay. So, but what I have drawn is a rectangle. Okay. I need to convert this into path. Okay. So for that, go to edit, convert to path. So now, if I have to, I'll just move it and show it to you. Earlier, it did not had this, right? So earlier it was just like this. This is the difference between path and the rectangle. So there is no middle line here. You can just see. I will just convert this one to path. Edit, convert to path. So this middle line started appearing. Okay. So this middle line should actually uh, coincide with your PR boundary like this. Okay, all these things should be properly aligned. Any minute, even a minute of minute mismatch is going to affect your layout. So I strictly recommend zooming it like this and viewing it and ensuring it whether it is properly aligned or not. Select this and press Q and keep it. The width should be 70 nanometer. Press 0.07, which is 70 nanometer. Okay, now again similarly press C, press uh, click on the mouse button so such that the middle button coincides with the x-axis or PR boundary like this. So now I have cut my poly like this. Now I have my metal one, and similar problem also happens to this. I have my metal one continuous. Imagine my one more cell is going to come here exactly from here. So these metals will be continuous, right? So I have shorted my poly and the LAACT layers here, and this will be shorting to some other output and input nodes maybe. That should not happen. How I am going to prohibit or inhibit that from happening is I will be drawing cut metal layers here. Okay, so first take the cut metal one, then first draw a rectangle such that it should start from the edge of the VDD. Okay, why I will tell you, and it should end at the edge of the VSS like this. Okay, so the reason why I took like this is I want my VDD and VSS to be continuous, and I don't want my the middle routing tracks to be continuous. The middle routing tracks should not be continuous, right? Only the VDD and VSS should be continuous. So now select this cut metal and again convert it into path. Edit, convert to path, and press Q and make it 32. If it is okay, it was 32 nanometer for me. So you make it, if it is not 32 nanometer, just make it 32 nanometer. Okay, so I'll again show it to you. Say it is some horizontal, some other width like this. Then what you have to do is just select this entire instance, go to edit, convert, and to path like this. Press Q and make it 32 nanometer. Okay, then move it. So as you can see here, it is not aligning. Sometimes this happens. Before that, you can see I had drawn exactly 32, so it was not happening like this. It was properly aligning. So sometimes this also happens. So you need not worry about that. You just keep like this, press Q, and then just delete that 5 here. At the end, there will be a 5. Just keep it 0.258 and 0.258. Press enter. Now you can see it is properly aligned. Okay, now keep keep a copy of this here. Okay, and then convert this to mask 1 and lock. Okay, then again copy this and keep it here. Press Q, select and make it as mask 1 and lock it. So right now we have drawn cut metals for mask 1. That means the metals with mask 1 will be cut here. What about mask 2? Right? So even we need to copy it again on both the sides and overlap it like this. Press Q and make it as mask 2 also. So now you can see I have mask 1, mask 2 overlapped here. Now I have only mask 1. Again I will be copying, or I can actually move that cut metal only like this and press Q and make it as mask 2 like this. Press F. So here you can see uh, everything is properly aligned, and I need not use this. I'll just delete that, and then I will just enable all the layers that I have used. Okay, so right now everything is done. uh, all the layers have been drawn, so I'll just switch on individual layers and show it to you how it will look. Before that, we just have to create pins, right? How many pins? 4 pins: VDD, VSS, VIN and VOUT. Okay, so for that, just press Ctrl P and then type caps VDD, VSS. Then we have to also create label. Okay, then go to options, keep height as default, everything else is default, just change the font to Roman, press OK, and then VDD VSS is of input output type only, so I will keep it this type only as of now. But before that, I should be drawing this pin layer in M1 pin, right? So uncheck the used and type here M1 pin, select M1 pin and come over here and enable only M1 first, and then select M1 pin and then start drawing your pin. This is my VDD, and I'll keep the label at the center like this. Now again I will draw VSS to the entire metal like this and keep my VSS label at the center like this and press F. Now again what I have to do is I have to create um, pins for V in and V out. Again Control P, type V in, V in, V out, we can't type both together because they are of in different IO types. V in is input, so everything options the Roman is there. Press OK and hide. Now I will be drawing. This is my as you can see I had put that M1 to LI PO via here, that is appearing here. Okay, so I know this is my input net because of that. So I will be drawing my V pin here, V in pin here, and I'll keep it V in like this. Then keep it um, output V out. I need to draw and make it as output. Click hide. Press this. Keep the label in the center like this. So you have VDD, VSS, V in and V out pins drawn ready. So now we have these metals which are unused. So I'll just select that and delete. Okay. So while selecting, be careful. So you should not be deleting any instances or wires like this. Um, okay. So like this, you will be creating your inverter layout, and I will just summarize all the steps that I have discussed in this video from the beginning once again. So you will be having initially the empty black screen. First, what you will draw is all the metal layers you will be drawing horizontally. All the metal layers will be drawn, right? Then you will color the metals alternatively, M1, M2. VDD and VSS should be in mask 2, and the thickness of VDD and VSS is 80 nanometer, and thickness, sorry, width of the metal 2 is metal 1 thickness of sorry, width of M1 metal 1 horizontal strips will be 32 nanometer, all the routing tracks in between except VDD and VSS which are 80 nanometer. Once that is done, you will draw PR boundary like this. Okay, then after once PR boundary is drawn, you will draw poly pitch line, this one, such that it will start poly pitch is how much, 86. So the PR boundary should be midway between these two poly pitch line, and here also the PR boundary should be midway between these two poly pitch line. Okay, so that means here it will be 43 nanometer away from y-axis it will be starting, and here you have to end it after some poly pitch line, and then it was, if you remember, this PR boundary was outside and I just stretched and here such that it is exactly midway between these two poly pitch lines. Then instantiate your pfet and nfet. Okay, and once you instantiate pfet and nfet with required number of fins, you will be enabling only nvel and draw nvel such that it covers the nvel of the instance exactly like this. It should cover the entire nvel. It should not be like it should not be like this. Okay, that will be a mismatch or not a proper way of doing. So that will lead to DRC errors and all. So you should not do that. It should enclose exactly like this, and the height of the NL will be half of the height of the half of the height of the cell, that is 0.408. From here to here it is 0.408. Similarly, for PSVT and NSVT you will be drawing like that. And once you draw all this, what you will do is you will draw cut poly. First you will draw poly like this, and then you will draw cut poly to actually separate the polys from adjacent rows. Okay, then you will join all the terminals. LACT will be shorted, and here the source terminals and the of the PFET and the NFET are connected to VDD and VSS respectively, and then you will create the input by um, connecting. You will actually uh, connect the input gate terminal to this metal horizontal strip by using via M1 to LiPo via. And similarly, the output node is connected to the one more horizontal metal strip like this using M1 to LiACT via. So in these two vias, you can also lock the to metal one layer to actually color the metal one layer like this, because this is mask to, right? So this also has to be masked to. Press OK, and here also I'll select the via, press Q, then go to mask to and lock it like this, right? So even if you don't lock, it won't create any problem, but it's always good to lock it. Okay, so once that is done, then you will be drawing your cut metal like this. Okay, so you will be having both cut metals here. You are not using any um, uh, horizontal metal strips which are mask one color, which are red color. For that reason, you should not delete the cut metal one of mask one layer. Okay, so it should be there everywhere. Uh, in some of the cells, this is very simple, right? So you are using only two metal tracks, two horizontal metal tracks. So for example, in D flip-flop or NAND gate and all, you will be using many horizontal metal tracks, metal one tracks will be used. Okay, so that's the thing about this. Then uh, enable cut active. You can just see your active area and cut active. So just to avoid the formation of transistors, you have cut active on the exactly below the edge polish. Here in the formation of transistor should be avoided, right? So you have cut active here like this. And finally, after everything, you will be drawing pins like this. Control P is the bind key for creating the pin, and then you will enable the create label option. Okay, and then you keep the font as Roman, then rest everything you can keep it default, and then type the name and click on the corresponding IO type, and then click hide and create the pin such that the uh, mm, corresponding pins should be entirely covering the net. It should cover entire net. Okay, but one more thing that I need to mention is you enable the cut poly. Okay, but this pin should extend from this cut poly. It should not be, should not be overlapping the pin metal. I will just enable pin and cut poly. So it should be like this. The pin should not, here it is fine because we are not cutting VDD and VSS. But here, as you can see, the pin should not overlap with the cut poly. Okay, so it should extend from cut poly to cut poly, but whereas if you have metal one, it will be extending from PR boundary to PR boundary, and then you have the midline of the cut poly coinciding with the PR boundary, and it will cut the metal like this. Okay, so this is how you create the layout for the inverter 1X using the standard cell approach. And that's all for this video. Thank you.